Lecture 3, Forecasting, Section 1, Part 2. So in order to have the models, let's first have the notation that we are going to use in the models. The observed values of demand during the past periods will be shown by D. So D1, D2, and DT. So DT is the demand at time T. And in order to show the time series, we can show the time series by this. So dt for t greater than or equal to 1. Okay, and if we are going to forecast at time t, so we are at time t and we are going to make a forecast. This means that since we are at time t, we know the demand of time t, so we are going to make a forecast for demand of time t plus 1. So we assume that demand at time t, demand at time t minus 1, and so on are known, but not dt plus 1. So we are going to make a forecast for demand in the next period, which is t plus 1. Okay, and so we show the forecast value by f here. So f will be the forecast value, and here ft minus tau and t means that we are at period t minus tau, and we are going to forecast the demand of period t. Okay, so yeah, we are at period t minus tau, and we are going to forecast demand of period t. And special cases tau equals to 1. So here, if we have ft minus 1 and t, this means that we are at time t minus 1, and we're going to forecast the demand at period t. Okay, so usually we show the forecast value as a function of the past observations, the past value of that variable. So for example, like this. And so yeah, it's a linear function of the past values, and we are going to consider a weight to the value of each past period. Okay, and in the time series models that we have in this chapter, we are going to distinguish on the choice of the weights, on assigning the weights. So different methods will assign different weights on the past values. Okay, so yeah, we'll see how we can obtain these weights in different methods in order to have a better forecast with less error for demand in the future. Okay, now we want to see how we can evaluate the performance of a particular forecasting method. So what are the criteria to compare the performance of different forecasting methods? So here we'll consider the error, and the error here we showed the error by E at time t, at period t, and so the error will be the difference between the forecasted value and the observed value. So if we are considering multiple steps ahead forecasting method, so ET, error at time t, will be ft minus tau t minus dt. Or if we have one step ahead forecasting model, then ET will be ft minus dt. Okay, so here for simplicity, f, let's say t minus 1 and t can be replaced by just ft, one step ahead. Okay, so yeah, in general, the difference between the forecasted value and the observed value, or the actual value of demand, will be the error term. Okay, so if here we have n periods, and for n periods we have the forecasted value and also the actual value, the observed value. So then we will have E1, E2 up to En. We will have n error terms, right? So now we can calculate our measures. So here we have three measures: mean, absolute deviation, or MAD. So it's a mean over the absolute deviations, and or mean squared error, MSE. So it's mean on the squared values, and mean absolute percentage error, or MAPE, MAPE or MAPE. So yeah, as you see here, we are making mean over the absolute percentages. I mean, EI divided by DI. Okay, so yeah, we have three measures, and by calculating these three measures for different forecasting methods, we can compare, or we can evaluate their performance. Okay. Let's have an example here. Here we have two plants, and the manager of the two plants have provided their forecast for 6 weeks, and also we have the actual demand or observed demand for those 6 weeks. So now we can calculate the measures, I mean the performance measures, and then we can see which plant has provided better forecast. So here P1 is the forecasted demand for plant 1. O1 is the observed demand for plant 1. So we can calculate the absolute value of the error, and then a square value of the error, and the absolute value of the percentage, E divided by O, error divided by the actual demand, and also same for plant 2. Okay, so by having these values, we can calculate the performance measures: MAD or MAD, MSE, and MAPE or MAPE. So as you see here, we have the MAD, MSE, MAPE for both plants, and if we just consider the MAD criteria, we see that plant 1 has better performance than plant 2. Or if we consider MAPE, again, same. Plant 1 has slightly better performance than plant 2. But if we consider the MSE here, mean of squared errors, we see that plant 2 is providing better forecast than plant 1. So, so so as you see here, we have three measures, and two measures of MAD and MAPE are offering that plant 1 has a slight edge against plant 2. But based on MSE, manager plant 2 has better accuracy. So what's the reason here? If uh, if we consider the errors in the table in previous slide, we see that the maximum error, which is 7, belongs to plant 1. And since in MSE we are actually considering the S-square values, so this measure is more sensitive to large errors, right? So because of that, plant 2 actually has better performance than plant 1, because the maximum error, which is 7, belongs to plant 1. Okay. One of the main properties of a forecasting method is being unbiased. So yeah, I mean, a desired property for any forecasting method is it should be unbiased, and this means that the expected value of EI, I mean expected value of the errors, should be 0. So in order to evaluate this property, we can plot errors over time. So if there is no pattern on the errors and they are fluctuating above and below the 0, then and it looks like random, then we can conclude that that forecasting method is not biased. It's unbiased. But if we see some sort of a trend, a special pattern in the errors, then it can't be unbiased, right? And one alternative way here is just computing the sum, not the absolute value or squared value, just the sum of the values of errors. And if the sum is too far from 0, then that method is biased. But if it's so close to 0, then we can conclude that we can say that that method is biased. Okay. So we are going to have the forecasting models from now on, and we start from the stationary time series. A stationary time series has this form: dt equals mu plus epsilon t, and here mu is a constant and epsilon t is a random variable with mean 0 and variance sigma square. So this means that, as you see here, mu doesn't have t subscript, and this means that mu is constant. So if we have a series of data over time, but the average, the mean over time is constant, and if we see fluctuations on the data over time, that's because of the variance. So, and in this case, we call this time series as a stationary time series. And the two common methods that are used for forecasting on a stationary time series are moving averages and exponential smoothing. Okay. The first method that we have here is moving average. In the moving average method, we take the arithmetic average over the n most recent observations. Okay, so for a one step ahead here, ft forecast for time t will be just a simple or arithmetic average over the last n observations or last n demands. And as a notation, we show this model as MA of n. This means that it's a moving average, and we are considering n last demands, okay, or observations. So how about multiple step ahead forecast? So since the moving average is based on the assumption that demand series is stationary, so is there any difference between one step ahead forecast and multiple step ahead forecast here? What do you think? There is no difference, right? So yeah, since it's based on the stationary assumption, the average, the mean is constant over the time. So the forecast of multiple steps ahead and one step ahead in moving average is exactly the same. Okay. Let's have an example here. Here we have the quarter 8, the past 8 quarters, and also the number of engine failures. Okay, so if we consider the moving average of 3 periods, then the first 3 periods will be used to forecast the failure for the next period, which will be period number 4. And then for period number 5, we will consider the last 3, which will be this, right? And again, last 3 for period 6. So this is why it's called moving average. We are moving the number of periods over time that we consider to forecast the next period's value. Okay, and also for the moving average of 6, as you see here, the first 6 observations will be used to forecast the value for period 7, right? So this is how the moving average works, and as you see here, we do have the errors for moving average of 3 and moving average of 6. So yeah, I mean, if we have historical data the time series of the past periods, then we can try different moving averages by 3, 6, 4, 5, or any other number here. I will see which one actually provides better result by comparing the error measures, one of those, or all the three measures that we have in this chapter. Okay. One of the disadvantages of the moving average is a recalculation of the average anytime that we have a new observation. So anytime that we have a new observation, so we need to recalculate the average based on the last n observations, right? But after doing some algebraic operations, we can simplify the moving average formula to this, as you see here. So the forecast for t plus 1 can be calculated based on the forecast for t and the observation of t and t minus n. Okay, so yeah, that's this is another way to calculate the moving average if we have the value of moving average for the past periods. Okay. So we told that the moving average is the method that we can use if the time series is a stationary time series. This means that there is no trend and the average should be constant over time, and we just have random fluctuations over the mean over the time. In that case, definitely moving average is one of the best methods that we can use in that case. But what if we have trend? Let's see. In this example, we assume a time series that there is a definite trend in the data. Okay, and we are considering moving average of 3 periods and moving average of 6 periods here. And as you see here, this is the trend, I mean the actual data observation, and this is based on moving average of 3 periods, and the other one is based on the moving average of 6 periods. And as you see here, the forecast obtained by the moving average is always behind the trend, right? Behind the trend. So this shows that the moving average is not a good one, is not appropriate method for the case that we have trend. But if there is no trend and the mean is constant over time and we have just random fluctuations, then definitely a moving average can be applied there. Okay.